example of the plan extract element. Okay? So rather than going through the usual way of derivations, so I shall take one example for uniform deformations to show you that how you can use your plane strain element for the calculation. Okay? So it's going to be similar to what you had here. Okay? So this one will show you the uniaxial locations, and then there are many calculations. Okay, but to you it might appear to be quite abstract. But anyway, let's work out one example. Then you come back to have the feeling. So rather than going through the individual step, now I go this example. Okay, so now this is going to be a very simple problem. Okay, what is the elongation of the plate? Okay, in this case, you call it a plate. Okay, rather than membrane. Okay, but if you have a membrane, when you subject it to constant force. Okay? So if in the model here, this is a rock. Okay? It is subjected to F. Okay, how much is the deformation if you fix it on the left hand? Okay? So can I get the answer? So how much is the deformation at the tips? Okay. 来，欧洲同学，一根杆，末端比例多少？ So if this is U1, this is U2. How much is U2? Okay, yeah, you're right. Okay, you learn some Hooke's law. Okay, your U2 is F over K. Okay, so this is what you learn. Okay, also another important thing here is you learn about the deformations along the length. How much is the deformation along the length? Okay, you learn about that. This is U2 X over M. Okay, so this is the deformation. And then U1, this is very little, almost zero, but it increased toward U2. Okay, so this is the first case that you learn about a shape function. But here the important thing here is, for this model, this is the shape function. You can fully return it as U1, which is supposed to be 0, multiply 1 minus x over m plus U2 x over m. Okay? So meaning if you have a robot, okay, your U2, your U1 is moving by delta, and at the same time, you apply a force. So your U2 must be a fraction of this, the inference coming from the U1, okay, plus if you have obtained this is f of k, yeah, it might be due to the, I think I got the right ending point, okay. You might know U2 here, okay, that x equal to 0 is U1, and x equal to L is U2. Then my question is, at any point x here, okay, what will be the displacement? So, accordingly, we could have linear deformation, okay. This difference, U2 minus U1 is equal to F over K. At any point here is to be obtained like this. Okay? So this is our idea about the rod. Okay? But now we change to another example. If you now have a plate, okay? If you now have a plate, okay, how much will be the deformation when you subject it to the same force? Okay, how much is the deformation here? You might have 1, 2, 3, 4. Okay? U1 is 0, U3 is 0, V1 is 0, V3 is 0. And the question here is, how much is your U2? How much is your V2? How much is your U4? And how much is your V4? Okay? So before we do any solution, okay, could we have a quick guess? Okay. What is the K here? So what's the K here? For a plate. This is the for a rod. So what's the K for a plate? How about you? What's the K? What's the stiffness of the plate? No. Okay, anyway, answer is on the board. You get one. Okay. 进度是多少？反的进度。Okay, I'll wait for you before we continue. What's the K? What's the stiffness? 来，后面那位，就你了。来，你说进度多少？
要是1A数的话，
yes, correct. It is EA over M. Okay, but in this case, my A could be your V times the thickness. For a rod, your A could be your the diameter square times pi over 4. Okay? So it is going to be the same. Then my next question is, how much is the elongation of the plane? How much is the elongation? Hello. before.
F2 here.
F3. F3.
Okay.
Yes, correct. Okay. So you accept the question and you don't know how to answer. Please recall your mechanism and behavior. Anything logical, please write it out. Don't leave any question unanswered. If you answer it, it's 0 mark. If you answer this, okay, it's a pass. Okay? Yeah. So you see here, this is supposed to be the answer. U2, U4 is equal to F over K. By what? By Hooke's law. Okay? As I told you before, finite element is kind of like a defined analysis. If now I have such a simple element, the only answer that finite element can agree to is Hooke's law. Okay? So let's see how we model this. Okay? Okay? So remember, okay, we might have divided this element into two elements. 1, 2, 3, 4. Okay? And I'm going to use constant strength element. Okay? Okay. Can one of you tell me how much the strength along the length? How much is strength in this? Like, how much is the strength? How much is the strength? Strength is defined as the deformations over length. Okay? Then we're going to have F over K F. So we have F over EA over L times L. Then we have F over EA. Okay? If you go to see this, F over E is the axial stress divided by the modulus. Then this will give you the strength in the x direction. Okay, you see that? Okay? So now, how am I going to solve the questions? Okay? So I will write you the procedure. Okay? You know this is a Hooke's law. But what's the procedure we have? We have to define Ux, okay, as a shape function of a node. Okay? You might have node 1, node 2, node 3. Okay? U1 and 2, U2 and 3, U3. You could have V. Okay, in this case, this is X1. Okay, you have the N1, V1 plus N2, V2 plus N3, V3. Okay? The second step, you're going to find out what is the strain. Okay? What is the strain? The strain is del U del X. Okay? Let's write. This is epsilon X is equal to del U del X. Okay? Epsilon Y is del V del Y. And then gamma is del U del Y plus del U del X. Okay? So agree? This is still the strain. Okay? Remember your Poisson ratio sigma y over E. And this is sigma y over E minus Poisson ratio sigma x over E. And this is your shear stress over G. Okay? And what is your shear stress over G? Your shear stress is, this is G is 1/3. Okay, is it? E over what's that? 2 plus 1 plus E. So this is what you have. Okay? We're going to do the inverse to obtain these expressions. So you can already see okay? So this is the expression. This expression is going to be E over 1 minus E squared. And then this is 1 E0, E1 0, and then 0, 0, 1 minus E over 2. So how do you get your K value? Okay? You have this strain versus okay. And this one you can also do the expansions. Okay, sigma x is equal to del n1 del x to 1 plus, because sigma x is your del u del x, and that's why it's going to be the derivative of the space shape function with respect to x. Yeah, please rewrite this at least once. Okay? So you got a feeling what this is. And then your gamma, okay, is del u, del y plus del e, del x. Okay? This is the sum of what do you do here? What you do is just a derivative along the x direction. This is a derivative along the y direction. And this is the shearing to find the gamma. Okay? Except now, this is partially distributed. Okay. So if you're doing a coding, what would you expect the answer? You would expect your elongation and negative. Okay. For sure, the majority of the strain is this one. Okay? This is the most dominant one. How about the rest? You might also have the necking in the y direction. And at the point here, you could possibly have the shearing, because I'm supposed to be a square one, but because of these deformations, okay, I could possibly have the shearing. Okay, so this is the shearing. Okay, let's come back to the question here. Okay, what is the shape function? And how do you obtain all that expression? Okay. Okay, so let me do this shape function first. Okay, how do I approximate the shape function? I told you before, okay, if this is zero displacement, what would be the deformation here? How would you interpolate the answer? Okay? If you draw, I think last week we draw it before, it's going to increase, okay, toward non-zero. Okay? So this is your uxy. Okay? So if I draw it in the 3D view, okay, this is my U2. Okay? Imagine this is the extended one. This is also U2. Okay? Your answer, your shape function is like a slope. Starting from U1 equal to 0, U2 equal to 0. Okay? This is the kind of shape function you can expect, because it's so simple. Okay? But apparently, the reality could be more complex. We might accept the fact that your U2, okay, might not be equal to U3, might not be equal to U4. Okay? So let's see another element. How about your element? Your element here is tricky. You have U3, U4, U2. Okay? If I draw it here, then the shape function will appear to be a equal slope. Okay? But you cut it, this is a triangle. So you're going to have other part. Dash. Okay, this one. Likewise, you do it to be half. Then the slope is going to be something like this. Then the question here is, how do I get that? Okay? Of course, last week we teach you about the approximations. A0 plus A1 x plus A2 y. Okay, is it? Yeah. Let's go back to our determination of the shape function. Yep. So we will use this. So in this case, how to find the A0, A1, A2? I think we take the example here. U1, U2, U3. You have your U1 is equal to A0 plus A1. Okay, how do you define it? Let's see. Okay, in this case, my naught. Okay, I define if this is 0, 0, and this is your width or your height, and this is your length. Okay, I'm going to do the substitution to show you. So this is my U1 is 0, and then my, okay, it's still U1, my height, okay, then U2 is A0 plus A1L plus A2H, and U3 is A0 plus 0 plus 0. Okay. So with this, then we move on to find what is your shape function. Okay, look at here. I have my U1, U2, U3 is equal to my A0, A1, A2. The first one is 1, 0, H. Second one is 1, L, H. And third one is 1, okay, 1, 0, 0. Okay. The sequence you are doing now is something like this. Okay. That sequence is different from the other way around. Okay. If you do the other way around, you're going to have a different sequence. Okay. Anyway, I just use this sequence. My question now is, would I be able to find this expression? substituting my normal coordinate. Okay? So I think this should be quite straightforward for you. Okay? What is my A0? My A0 is, if you do the inverse, 1 0 H, 1 L H, 1 0 0. And then A0 is the first variable, so my unknown is replaced by the displacement U1, U2, U3, and then this one is 0L, H, 0, 0. Okay? If I'm using the square, I mean this is going to be very simple. Anything is I'll just take this. Anything is 0, except the first one and their cofactor. Okay, positive, negative, positive. If it's positive 1 and the cofactor, okay, then this is going to be negative LH. Okay? How about this one? Okay, the only non-zero thing is 3, and then again 0H and LH. This is minus LH U3. Okay, the first variable is U3. Okay, and then the second variable, the second coefficient, you replace the second column to be U1, U2, U3. The rest will remain. Okay. So for me, I'm still doing this same thing. Okay, 1 times the cofactor U1, U2, H. Okay, and then plus this is minus U3 times cofactor 1, 1, H. Okay, and then divided by minus LH. The second column is, the second term is 0. So you're left with what? You're left with the U2 minus U1 divided by LH, and then times H, is it? Okay, we've got to check this variable. Okay. LH. Yeah. Yeah, A2, you see that after your simplification, it has a unit of what? Previously, this has a unit of displacement. This one is N over N. Okay? The coefficient here is, this is meter. The coefficient here is N over N, because you are going to multiply with your X again. Okay? And likewise, how about your U3? Let's see. U2, you are dividing everything the same. But now the third row, third column replaced by U2, U3. And divided by the minus LH. Okay, in this case, I will take this cofactor, plus minus plus, because that row is all 0. This is L and the cofactor. The cofactor is U1, U3. This is your L. What's that? L times what's that? It is U3 minus U1. Okay. And then divided by minus LH. This minus LH. So in that way, ux is equal to u3, and then this is minus u2 minus u1l times what? Times x. And then this one is, okay, this is it minus? Oh, sorry, let's see, this already changed already, is it? Yeah, this is plus already. Now this is plus minus, okay? And this one is the plus u1 minus u3 over h 1. Okay. So in these expressions, so let's do some grouping. Anything to do with the x, please take it. u1 and 1 over h minus x over l. Okay, and then anything to do with u2 times x over l. Anything to do with your u3, it is 1 minus y over h. Okay. By taking this example, okay, do you see that? What is my shape function for the piece of 1, 2, 3? Okay? If I'm talking about displacement u2, okay, you can see the shape function for u2. Okay, the inference is going to be, this is n2, n2 is going to be do you see that? N2 is what was there predicted. Okay? Of course, yeah. If you look at the contribution here also. Okay. U1 along the line could also contribute, okay? Yeah, but I think the expression is different, okay? And then how about U3? If it happens this one is 0, the inverse is not there, okay? But at least from this exercise, you can see that you can capture this, okay? But are we going to do that? Yeah, this is just give you a flavor of first-hand experience. Okay, but we are not going to do that in your actual calculation. In this case, we're going to find the force balance with the internal spring force. This spring force has stiffness matrix and displacement vector. And take this for example. Okay, my writing could be different from you. Okay, but I think that's fine. Okay, U1. Okay, the left hand is fixed. Okay, U1, U2 is fixed. U3 is free to move. And 4 is free to move. Okay. And then here, what are we going to do? Okay. What we're going to do next is we're going to find out what is the area of this triangle element. It is basically the determinant by substituting the expression. Okay, you have 1 that is 0, 0, and then 2, that is, okay, depending on what you're writing, okay, yeah, this is LH, yeah, anyway, so anyway the area is half the height over L, yeah, half L. And then finally, next, in the operation here, we wouldn't expect you to do full expressions because your K is going to be very complex. Okay, this is the B matrix that defines the relationship between strain and displacement. Okay, how about the stress? Stress is the constitutive matrix times strain. Strain is B matrix times displacement vector. The operation is there. Then next, you're going to find the transpose of B matrix times D, and then times B, times T and A. This is how you find your stiffness matrix. Okay? The operation you can see already, it is very tedious. So in the final exam, we're going to computing room. You can use MATLAB. Okay, symbolic. Okay, so this is the kind of operation. Okay. And then next, and you're going to find so many things. So this is rather complicated. Okay, so how would you be able to find the eventual displacement? Okay, you look at node 3 and 4. Okay, so you have to handle element 1 and element 2. Okay, element 1 will have these force equations. Okay, yeah, U3, V3 for these tip nodes. And then next, the element 2 will contribute you to another force balance. This is going to be U4, V4, and then U3, V3. Okay? So you can clearly see that this is not easy. Okay? But it's solvable. So when you have these reductions, okay, then you have the 4 variables to be solved. Okay? Yeah. So as for the start, I think let's come back the simple operation here. Okay? If you want to solve the real element, you can see that there are so many elements, so much of stress. How could you solve it? Yeah, every element are subjected to one constant strain. Okay, how are you going to solve it? I think it's quite difficult. But what you can do is you can do element by element, step by step. Okay, so take this for example. Okay, how do you find the matrix here? Okay, what's a B matrix? Okay, B matrix is the one that helps you to find the strain. Okay, so there are some conventions. Okay, how do you memorize the determination of the B matrix? Okay, let's come to this. You remember this constant strain triangle, not 1, not 2, not 3. Okay, their displacement can be interpolated by shape function. Okay, how do you get the shape function? We obtain this shape function. Okay, so these shape functions, you might find that it's difficult to figure out, but it could be meaningful if you see from the expression here. Okay, what is n1? Okay, n1 is the shape function when you are standing at not 1. Okay, so you can see that at that point it must be equal to 1. Okay, so what you have there is a constant plus linear function of x plus a linear function of y. Okay, but these coefficients, please bear in mind, these coefficients is independent of the not 1. Okay, so let's try to understand the shape function now. Okay. You must have the first-hand experience or impression of the shape function first. Otherwise, it's difficult for you. Okay, all our expression here is specific. Okay, by substituting the coordinate there. Okay. But if you want to generalize, okay, any point okay, when you draw like that, this sequence is counterclockwise. Okay, your U1 is A0 plus A1 S1 plus A2 Y1. U2 is A0 plus A1 S2 plus A2 Y2. U3 is A0 plus A1 S3 plus A2 Y3. In the matrix form, we have U1, U2, U3 is equal to a matrix multiplication with the coefficient. Okay. This is 1, x1, y1, 1, x2, y2, 1, x3, y3. Okay? So this is what is obtained before. Okay, and then now, if you want to find what is your U1, okay? Yeah, sorry, you want to find what is A0, okay? You are obtaining something like that. And then replacing this with the first column. Okay. So this one is your yeah, the answers will be very tedious. Okay, I will go through that. That's in your notes. Okay. And then next, after you have everything, this is your shape function. It's very tedious. As a coefficient, okay? And then you substitute in, you do the grouping. You have the shape function, something like But we do pay attention to how this is related. One, two, three. Okay? Your shape function 1, if I know, if I'm going to draw that, it's going to be a plane like that. Okay? See from the point 1. Okay, let me draw this. Looking from these, how do you write your shape function? Okay, you see, your shape function 1, okay, is 1 over 2a times a constant, okay, and this constant is, you can say this is your x2, y3, and then this is your x3, y2. You see this? And then second term, okay, is your 1, okay, y3, y2, 1, x. And then last, what's this? 1, 1, this is x3, x2, okay, 1. Okay, to make it consistent, you write down y2, y3. Okay, x. One feature here is shape functions is something divided by the area, okay, times this thing. This thing has a unit of meter square. This thing has a unit of meter square. Okay, so one way of memorizing this is the sequence. Shape function 1. Then this one is x2, y2, okay, minus x3, y2. So 1, 2, 3, 3, 2, okay, and then next. If you multiply x being the first coordinate, okay, it's going to be first coordinate times y2, y3 plus second coordinate, then yeah, this one multiplied with x3 minus x2. Okay? Yeah, so prepare your own formula sheet for later use. Okay? And then likewise, n2, the shape functions, okay, is 1 over 2 times the area times the constant. Okay, this constant is obtained from 2, 3, 1. Okay? So how do you have that sequence? If you have 1, 2, 3, the sequence is counterclockwise. So it is 1, 2, 3. And then if you are starting at 2, you are also doing the same counterclockwise. But this time around it is, yeah, 2, 3, 1. Okay? So likewise, your this expression here is about the same. Okay? Yeah. And how about your entry? The constant part is 3, 1, 4. 3, 1, 2. Okay? So these ones, your whole expression is obtained inconsistent with the sequence of your knot. So you have 1, 2, 3. If you reverse the order, you will have changed the sign. Okay? So please bear in mind when you try to use this formula with reference to this, you do the more sequences in counterclockwise. Okay? If you want to use that formula. Okay? You cannot do the jumping of the knot. If you do the jumping 1, 3, 2, okay, you're going to have a sign difference. Okay? So this is the part that you have to bear in mind. Okay? And then all these shape functions add up to be 1. Okay, and then next, the strain, as we derived it before already, you express it in the matrix form. There are two ways of writing this strain and B matrix. It depends on the displacement vector you are writing. Some textbook writing all horizontal displacement for knot 1, knot 2, knot 3, and then vertical displacement for knot 1, knot 2, knot 3. Okay? So your B matrix, the shape function derivative, shape function derivative 1, shape function derivative 2, shape function derivative 2, 3, followed by 0, 0, 0. Okay? So this is one form. Okay? Another form is you take the horizontal knot, horizontal displacement followed by vertical displacement for the same knot. And then for knot 2, horizontal displacement, vertical displacement for the same knot 2. And then next, horizontal displacement and vertical displacement in the same knot 3. So in that case, the shape function derivative will be shape function 1 derivative followed by 0, shape function derivative 2 followed by 0, shape function derivative 3 followed by 0. Okay? And so for the sequence of the vertical strain, then you have 0, shape function derivative equals to 1, and then followed by 0, shape function 2 with respect to y, and then followed by 0, shape function 3 with respect to y. Okay? So, and then next, one thing that you take note of, you might find that this expression should be quite complicated. How about the third row? Third row is you are having the shape function 1, differentiate the shape function 1 with respect to y. So this is kind of like the swapping of the order for the same knot. Okay? This one comes to here, that one comes to the second column, and then the fourth column comes to the third column comes to the fourth column, and then this is the sixth column comes to the fifth column, and the fifth column comes to the sixth column. Okay, this is the way you have a shorthand or logical memory how this is right. Okay, after you have this, your B matrix is for the first row. It has to do with knot 1. Okay, let's say U1. So at U1 the coordinate is x1. Okay, so this coefficient is y2 minus y3. Okay, and then likewise this one is y not 2. Okay, then this is y3 minus y1, and this one is for not 3, then it's y1 minus y2. So you will see the coordinate expressions when you are at the particular node. Okay, at knot 1 you will see the coordinate 1. At knot 2 you will see coordinate 2. At knot 3 you will see coordinate B matrix here, remember, in this case is the cluster sequence of horizontal displacement and not 1, 2, 3. Okay? But your B matrix, okay, for this, okay, is going to be expressed differently. Okay? So this is the clustering of horizontal displacement for 3 matrices. Clustering. Okay? A shorthand of the writing is 1, 2, 3. 2, 3, 1. 3, 1, 2. Okay? This is for displacement 1, so you will multiply them in y. Okay? And then for this one is this for displacement in vertical directions. The second row function is multiplied with the difference of x, 3, 2, and then 2, 1, 3, then negative. Okay, and then this one is 3, 2, 1. Okay. So and then we do the swapping of the column. Okay. If there's just now the sequence is counterclockwise, but the displacement is clustered for 3 nodes. But in this case, if you don't want to cluster all the horizontal displacement together, you're going to have alternating of the horizontal vertical displacement. Then the non-zero coefficient will become alternating. Okay? You have non-zero 1, you have 0, you have non-zero 1, 0, you have non-zero 1. Okay? Okay, so, okay, what happens if you now reverse the sequence? Rather than doing the counterclockwise, you have the clockwise sequences. You see your coefficient. The coefficient is negative for this filter. Okay? So you can stick to 1. Then the B matrix will change its sign. Okay? Okay? They're going to give you the same answer, but because of this order sequence, you're going to have the change in the sign and the coefficients. Okay? And that's how you get your concentric triangle. Okay, then next, how to find the numerical example? We take this example. So in this case, you have a length of 75 millimeters, and you have a height of 50 millimeters. What's the area? Okay, it's the length and height divided by 2. What is 2 times the area? This is 75 times 50. Then you have the 3,750 millimeters square. And then next, how do you get your B matrix? The B matrix is, if so, as you can copy down the equation here, then do the substitution, okay, and then you have the expression. So that's why, please prepare your own formula reference, okay, in the final examinations. Okay, you need to know that this sequencing must be counterclockwise for this particular equation. Okay, and then next, how do you find this B matrix for element 2? Okay, you can do the same. Okay, and then next, what you have next is the strain. Okay, stress. Okay. Stress is related to the strain by this multiplication of D. D, as we obtain here, is something like that. Yeah, you're going to do the exercise. How to find the strain, stress in the x direction, y direction, and the shear stress. Okay. For this multiplication, it's very simple. Just take out the constant out. It is E over 1 minus B squared times 1 over 2A. So you take it out. And then next, you do the multiplication of the 2 matrix. This is the 3 by 3 matrix and 3 by 6 matrix. So 3 by 3 times 3 by 6, in the end, you're going to obtain 3 by 6. So the first one is, first row, 1 and b times y2, 3. So end up we have y2. And then first row, second column, then you have vx3. First row, third column, okay? Then you have this 1 minus b over 2 times x1, 3. Okay? Is it? And then first row, yeah. Yeah, so you complete the row. First row, first column, okay? Yeah. Okay, so now for the first row, first column one is you just take whatever on the top. First row, second column. First row, third, okay, is y31. First row, and then fourth column, then you have bx3. First row, fifth column, you have y12. First row, sixth column, you have bx21. You do the same for the second row. You're going to have this expression. And then next, you do the same for the third row. First column. The third row are all pre-multiplied by 1 minus b. You can put them out later. Okay? So this is how you obtain your b times d matrix. It is b times b. Okay? And then there are this 3 by 6 matrix is then going to multiply with the displacement vector, which has a size of 6 by 1. Okay? So the stress we obtain is based on Cartesian coordinate. You have stress in the x direction, stress in the y direction, and then shear stress in the other 3 directions. Okay? But if you want to find the principal stress, then you have to find the principal angle, which is the arctangent of 2 times the shear stress and the normal stress difference. Okay? And then in that way you can find the maximum stress being the average of the 2 normal stress plus the square root of the average of the normal stress squared plus the shear stress squared. So this is how we determine the maximum principal stress. Then next you can find the minimum principal stress. This is the average normal stress minus the square root of average normal stress squared plus the shear stress squared. Okay, this is what you obtain for the Mohr circle. Okay, so this is how you define stress. Then next, how would we be able to find out the K value? Okay, to find out the K value, we're going to use the potential energy method. This is the total strain energy, total potential energy equal to the strain energy minus the work done by external force. What kind of force could you have? You could have body force, you could have traction. Traction is the force on the line, and then you have normal force P. Okay? So if you want to find out the displacement, it's very simple. Just do the derivative of the total potential energy, then you're going to have a force balance. Okay, but before that, let's have a look on the expression for the strain energy. The expression for the strain energy is the strain vector transpose times the D matrix and the strain vector. But you remember what is strain vector? The strain vector is B matrix times displacement, normal displacement. So the transpose of this would then be the displacement vector transpose times the B matrix transpose. Yep. So interesting thing come here. Okay, how do you find the force vector? Take for example, if you forget about the body force, FB, and forget about the traction force, you focus on the point force. The point force will be denoted as the force P here, force F here. Force F can be obtained by partial derivative of U1. Okay? So if I take U1 to be one of the force vector, displacement vector, okay, I can do the partial differentiation here. Then I'm going to have to see that, then we can do it here. Okay. Remember, for your K spring element, okay, you can express what's your strength energy. Your strength energy is half kx squared. This is u2 minus u1 squared. So remember this. And then your potential energy is the strength energy minus F1 u1 minus F2 u2. Okay? If you want to find the force balance, you just do the derivative of this with respect to u1. Then the first expression is k u2 minus u1, and then partial differentiate of del u1 del u1, and then plus what? F1. Okay? So in the first expression here, if the derivative of the total potential is 0, you have the F1 is equal to, F1 is equal to what? This expression. F1 is equal to del u del u1. You see it? So what I'm writing here is, I'm writing so many derivatives. Okay. If you do this sum in the vector form, okay, they are only non-zero at, let's say, not 1, displacement 1. Okay, so we do the partial differentiation with respect to u1. Okay, and then next, the non-zero forms in the vertical direction when you do the partial differentiations with respect to the vertical displacement of 1. So if you do that partial differentiation at each node at each coordinate, then you're going to have all the forces. Then all these force vector is obtained from the partial differentiation of the strain energy with respect to displacement u1, v1, u2, v2, u3, v3. So you're going to have these 6 by 1 force vector. They are obtained in the expression of B transpose D, B, and because this is the integration of the volume, okay, TBA. And in this case, because the strain energy is independent, the B matrix is independent of the coordinate, so you can take out the BTBB out of the integral. So as a result, you only integrate to the volume, that is the thickness of the local point times the area of the local triangle times the displacement vector. Okay? So this is how we got. Okay? So if you do that substitution in, then you're going to have coefficients B transpose D and B. Okay, this is going to be your element. Okay, what you end up is 6 by 6 matrix. Okay, if you're going to do like MATLAB, okay, you're going to have this kind of expressions. Okay, for your backup, you can copy down, but it's going to be very tedious. Okay, this is your constant strain triangle. And what is your beta and gamma? Go back to the previous calculations. Your beta and gamma here. This is what we call beta 1, beta 2, beta 3, gamma 2. what was expressed. Okay, so you're going to apply, okay, to the example, okay, you will see this. Yeah, one expression here is using beta and gamma. Okay, and another recommended expression is using y23, x3, 32. All this can be obtained like that. Okay, if you do the expansion, it's very tedious. Okay, so please get prepared. Okay, many of you still do not know how to use a MATLAB. For our case, we have the coding in the MATLAB, but yeah, please do it. Yeah. Yourself at home. You see this. Let's see. Okay, we'll pass you the coding, but you got to. Yeah, the coding will be there. Okay. And the symbolic calculation is yeah, somewhere not. And it's all yeah, where that code here. So that's that exercise. Yeah. Can you please solve these questions in ANSYS and MATLAB? Okay? And then the exercise is here. Okay, what's the coding look like? Yeah, this is what we have. And let's see the coding. I think next week you practice these questions. Okay, you have the element 1, 2. You have not 1, 2, 3, 4. Okay, first define the material property E, define the Poisson ratio, and then define the length, define the height, and define the plate thickness. Okay? And then next, define the coordinate 1, 2, 3 in counterclockwise order. So this is 0, 0 for node 1, this is L 0 for node 2, and this is L for node 3. So in this sequence, I, J, K. Okay? Yeah. And then next, you define your coordinate matrix. Node 1, node 3. Not 2, not 3, and then you substitute them into this function to obtain the K matrix. Okay, what is the function there? The function there is very simple. Yeah, there has the constitutive equations, which is the matrix, geometry matrix, and then once you get the coordinate, okay, what you need is to define and calculate the area. Okay? And then next, you need to calculate the B matrix. Okay, the B matrix, how do you obtain that? Okay, remember, node 1, now I represent as I, node 2 as J, node 3 as K. I, J, K. Okay, in my first entry, it is for node 1, so I, J, K. It's going to be Y, J, 1 minus Y, K. And then for node 2 is 2, 3, 1. So it is J, yki. The expression here is yki is equal to yk minus yi for the third column. And then for the fifth column, this is for node 3. Opposite one is going to be yij. So this is yij. Okay? And likewise, we can do the same for x. For node 1 is x, it's a jump because it's negative x minus xjk. And then next for node 2, it is the x minus xki. Okay? So, and then for the node 3, it is minus xij. Okay? So, in this way, we have these expressions. Okay? 2, 3, 3, 2. 3, 1, 1, 3. 1, 2, 2, 1. So the first coefficient for the first row is opposite in the order when you do these subtractions. And then next, and then you are doing for the third row, you are swapping the column 1 coefficient to the column 2. And then likewise